Who is a astrophysicist at the University of Lisbon. He's the director of the physics department at the university. We're outside on a stormy day in Lisbon.
That's right.
As luck would have it, I arrived this week when the weather was perfect, and now the weather is doing its thing. But anyway, we've been talking gravity waves, gravitational radiation, gravity, and black holes. And what is gravity, Vitor?
Interesting, Bruce. So gravity is too familiar for us. We're born and we die with gravity, so we don't think very often about it. It's the weakest of the fundamental interactions.
The four fundamental forces of the
nature.
universe, yeah.
And it's interesting because even though it's the weakest, it sums up. And that means that if I start adding matter, the gravitational interaction sums up, becomes stronger, whereas all the others, they just weaken. So on large scales of planets, stars, black holes, and the universe, gravity is the dominant interaction. So it actually dictates the behavior of the universe, the geometry of the universe, and the evolution of the universe from the moment it was born until today.
Which is amazing because you would not think it would have such effects over such large scales, but
That's right.
as the weakest of the four forces, but it does. And until recently, in '93, Taylor discovered by indirectly the gravitational ripples of space-time, and then more recently, LIGO and Virgo, and now the Japanese Kagura. These three ground-based gravitational wave detectors have opened a whole new vista on the way we look at the universe, and that's not hyperbole. So what will gravitational waves tell us about black holes, do you think?
Yeah, that's perfect. So Hulse and Taylor in the 70s started monitoring a couple of neutron stars orbiting around each other, and as they orbit around each other, they're accelerated masses, so they emit gravitational waves. These are space-time ripples, or they're simple traveling gravitational forces. They travel at the speed of light. Now, because the system is losing energy, as time goes by, the binary shrinks and eventually collides, and the Hulse and Taylor will collide in some million years from now. Now, the amazing thing about gravitational waves, first of all, we can detect them. Second, they are stopped by nothing. So they travel through the Earth interior, they travel through the sun, nothing stops them. So that also means that gravitational waves are hitting the Earth from all directions, from all cosmic times. And we're able to see them. So we're going to be able to study the interior of neutron stars, the region around black holes, and even the Big Bang, the moment when the universe was born. So all of this information is available for us. It's really astounding.
And you do not see black holes as a big bugaboo. You actually think black holes may be seeding life in the universe.
Oh yeah, but first of all, black holes are the big mystery out there. We know there's problems inside, in their interior, and gravitational waves may be the clue for those problems, for the solution to those problems. Second of all, it's interesting that many people think that black holes are just vacuum cleaners, the death, the destroyer of worlds. But they're not. They're very compact. So when matter reaches the region close to black holes, it moves at close to the speed of light, it collides, and most of it, or a fraction of it, gets thrown out, right? Gets expelled in jets. And this expelled matter is going to travel to the outskirts of galaxies, where it's going to form stars, planets, and who knows, maybe people like you and me. So actually, black holes are the beginning of life as well. Right?
So they're not to be you don't want to get too close if you are traveling in a warp drive spaceship, for instance. But they're not the big bugaboo that people think.
They're not. They're the big object in the universe, the mysterious life forming, the object that helps galaxies co-evolve. We have supermassive black holes, objects with millions of solar masses in the interior, right at the center of galaxies. We don't know exactly how they form. We know they sink through through friction, but the next decades are going to tell us how exactly they got to be there. We are going to know black holes much, much better.
And the European Space Agency's LISA spacecraft, which is under construction now, you mentioned, is going to be able to give us the resolution to see radiation, gravitational radiation, from our supermassive black hole at the center of our Milky Way galaxy.
Yeah, they're building this amazing device, something that's going to fly, so in space, arms, so they're going to, LISA has 3 arms of 2 million kilometers each, 2 million kilometers, and it's going to be seeing basically all of the observable universe, all of the supermassive black holes out there, perhaps, who knows, phase transitions from the beginning of the universe. It's an amazing new era, really. Gravitational wave astronomy is here to stay. It's going to be the last word, telling us how the gravitational interaction really works.
And you obviously love your job. It's 6 o'clock on a Friday.
On a rainy Friday.
On a rainy Friday, everybody else is out having a cocktail, and you're talking about gravitational wave
That's
astronomy
right.
in the cold and the rain. I really appreciate your time. Great to be back in Lisbon. Thank you so much, Vitor.
Thank you, Bruce. My pleasure.